6. Question 4 is about standing waves. Part 4a, what is meant by the superposition of waves? If you've not filled that part of the question in, just look it up in your textbook and copy it out of there. It's pretty much a learning thing that you need to know. Part B is very similar. Explain how a standing wave is formed by the reflection of a wave. Very frequent question. You have an incident wave, that wave is reflected, and then there is interference between the two. The kind of words you need to use in your explanation, and notice this is worth 3 marks, is incident wave, reflected wave, superposition, constructive and destructive interference, nodes and antinodes. If you mention all those, you'll certainly get 3 marks. Part 2, a standing wave is visible on the micrograph. What you need to do to answer this question is to realise that on the picture, if you count them up, there are 5 nodes, obviously with an antinode in between each one. If you then know that the distance between any 2 nodes, or any 2 antinodes, is lambda over 2, you should be able to work out that the distance, total distance between these two is 2 lambda. They then give you the total distance between the 2 points, x and y, on the graph, and so you should be able to work out the wavelength, and you should get an answer of 2.1 times 10 to the minus 9 meters. Part 3, draw a diagram. A couple of diagrams should suffice. One for amplitude, and you can draw a standing wave and explain which of the 2 points on there is the antinode. Again, if you're not sure, look it up in your textbook. Question 5 is a question about internal resistance, a subject which is usually not that well understood. This is your chance to understand it. Calculate the resistance of the bulb. Part 1, very straightforward question, R equals V over I, Ohm's law. Part 2, the cells form a battery with an EMF of 2.80 volts. You have to remember that EMF is what you would, the voltage that you would get out of a battery if you took a reading with a voltmeter across the terminal, so when no current is being drawn. So the EMF equals what you actually get out of the battery. So in this case here, 2.68 volts, and IR is the lost volts. How many volts are lost heating up the battery? So in this case here, they tell us that the EMF is 2.80. Above, we know that we have a terminal PD of 2.68 volts, and they tell us the current is 0.31 amps. So from that you should be able to work out the internal resistance of the battery. If you don't understand this equation, worth spending a bit of time because it crops up all the time. Comment on how well these values match the necessary conditions for maximum power transfer. It's just something you need to know. It may have been proven to you before, but you need to look at the value of the internal resistance compared to the value of the external resistance. Again, look it up in your textbook. Part B, each cell is labelled capacity 2 amp hours. A fairly straightforward question. You just have to notice that there are 2 cells, each of 2 amp hours, and use the equation Q equals IT, where T must be in seconds. If you do that, you should get an answer of about 14,400, which is close to the 14,000 coulombs that they suggest in the question. And then part 2, you just need to rearrange the equation above, T equals Q over I, where the value of Q you've just worked out is 14,400, and when you do that you should get an answer of 46,450 seconds. Part C, the internal resistance of the cells increase as they are used. Clearly from the equation we had above, if the internal resistance increases, this term will get bigger, and that's the lost volts. So more of the energy supplied by the battery will be used to heat up the battery rather than actually appearing across the terminals where it can be usefully used. Part 6 is a spreadsheet question. Part A, speed equals distance over time. You should get an answer of just over 15 meters per second. Part 2, you just need to look at a suitable formula. One of them that works would be E6 plus B7, but there are other different ways of doing that. As a graph next, you need to join the points with the best straight line that you can manage. And then, because it's a velocity time graph, the gradient of that line will tell you the average deceleration of the car, and you just need to draw a big triangle. So if you have your points joined on a line, make sure that you use the full extent of the straight line to do a triangle. Don't do a small triangle in the middle. Average braking force, pretty straightforward. F equals ma, you know the mass of the car. Part 2, the origin of the braking force is just to do with the friction between the brake pads and the discs. Parts C, 1 and 2 are to do with kinetic energy. You should know the kinetic energy formula, half mv squared equals kinetic energy. That gives you a value of 132 kilojoules for part 1, if you've done it correctly. Part 2 relies on you understanding the meaning of the phrase work done. In physics, work is done when energy is converted from one form to another. In this case, the kinetic energy of the car, given by a half mv squared, is converted into heat, primarily a little bit of sound, by the braking force supplied by the brakes over a certain distance d. And of course, when the brakes have done their job, all of the kinetic energy of the car will have been converted into heat in the brake pads, and the car will be at rest. So if you look at this equation here, you can see that that's the kinetic energy. If we were to plot a graph of that against the distance that the car travels, you should be able to use y equals mx plus c, although in this case c is 0, to work out why it is that the gradient of the graph is equal to the braking force on the car. And that's the end of the batch.